Okay, so this is the outline for chapter 32. Okay, so we will talk about the Gauss law for the B field. So in chapter 23, we already talked about the Gauss law for the E field. Okay, so this is another version which will be easier. Okay, because we don't have a magnetic dipole, magnetic monopole. I mean. Okay, and then we will also talk about the induced B field, and the displacement current. Okay, so yeah, you can consider these two are group. Okay, so in this case, we will add a term called the displacement current into the Ampere's law. Okay, then we will call it Ampere-Maxwell's law. So that's which is the complete form. Okay, and then in the second half of this chapter. All these are some hardcore physics stuff. Actually, I don't know them very well. So you try to regard it as listening to a story. Okay, so we will talk about the magnets. Okay, and then the magnetism and electrons. Okay, so how the B fields, or I should say, where does the B field comes from? Okay, and then finally we have three material called the dimagnetism, paramagnetism, and then ferromagnetism. Okay, in Chinese it is called 抗磁性、顺磁性，还有铁磁性一个叫抗磁性，一个叫顺磁性，一个叫做铁磁性ferro. Okay, so we'll talk about three material about the magnetism. Okay, so first we will talk about the Gauss law for B field. Okay, so here is the highlight. Okay, so it says the simplest magnetic structure that can exist is a magnetic dipole. Magnetic monopole do not exist. Okay, actually in previous chapter we already mentioned this several times. Okay, so we don't have a magnetic monopole, so we only have a magnetic dipole. Okay, so for the B field, but for the E field, we not only have electric dipole, we also have individual charge. We can have individual positive charge or individual negative charge. So this is the main difference, between the two types of source of the E field and B field there. Okay, so here it says the Gauss law for B field is a formal way of saying the magnetic monopole do not exist. Okay, so the law asserts that the net magnetic flux phi b through any closed Gaussian surface is zero. Okay, so it is actually written like this: phi b, which is this surface integral, equals zero. So I don't need to talk about what is a surface integral again, because you have already learned the surface integral in chapter 23 when we talk about the Gauss law for the E field. Okay, so at that time the Gauss law for E field is something like this: E naught or epsilon naught, and then integration of E dot dA equals Q enclosed. Okay, so when you try to transform it, okay, so this is, or you can write it as epsilon naught phi E, okay, like this. Okay, so when you try to change a formula for the E field to B field, okay, so you try to find some corresponding variable, like you change phi E into phi B, and then you try to change epsilon naught into 1 over mu naught, okay, not mu naught, 1 over mu naught. And in that case, this side will be 1 over mu naught, and then integration of B dot dA. Okay, so you may feel like, oh, we don't have this 1 over mu naught here because this is zero. So mu naught is not zero. Mu naught is not zero. So we can just multiply mu zero on both sides so that it vanishes. Okay. So we only have this thing left, okay? Because this thing to be zero, and then you intentionally multiply it by a non-zero value to be zero, so it doesn't is reluctant. Okay, so we just keep this one. Okay, this one could be a variable. Okay, so in that case, in the middle part, we have individual charge, so we can have net positive charge or net negative charge. So we have this Q enclosed, but we don't have magnetic monopole. So in that case, we have a 0 there. Yeah, because so it says that magnetic monopole do not exist. The law asserts that the net magnetic flux through any closed Gaussian surface is 0. OK， 所以它的意思就是说，这个Gauss law for B field 本身就是告诉你说 magnetic monopole 不存在。OK， 所以它就写成这个形式。Okay, so Gauss law for B field says that there can be no magnetic flux through surfaces because there can be no net magnetic charge. OK， 它用了另外一个不太正确的、不太规范的名称，它叫做 magnetic charge， 就是对应当是 electric charge， 就是电荷。电荷的话就是有正电荷、负电荷。那你那个 monopole 的话，你可以想象成它是一个磁的荷就是那个什么磁场的源头但是我们现实当中至少到现在还没有发现，从 Maxwell equation 到现在已经100多年了也没有办法找到这个 magnetic monopole 也没有办法找到 magnetic monopole 所以他就说there can be no magnetic flux through the surface because there can be no net magnetic charge, means the magnetic monopole, individual magnetic poles enclosed by the surface. OK， 所以这个很简单，我们就不需要再重复，因为关于计算的部分，你算电学版本的Gauss law已经算很多了，那就这个右手边等于0的话，只会让计算变得更简单，所以这里就没有很多的例题去讲它。Okay, so the next topic is about the induced B field. Induced B field. So in chapter 30, okay, we have learned the induced E field. Okay, in the Faraday's law. In the Faraday's law, we have induced E field. So here we also have induced B field. So it says a changing electric flux induce a magnetic field B, and then this is called the Maxwell's law. Maxwell's law. So on the left side, okay, very familiar with it. So this is the left side of the Ampere's law. So integration. Okay, so this is the line integral. I don't need to repeat because you have already learned the Ampere's law. But on the right side is different. Okay, on the right side it said that we have this mu naught epsilon naught, and then we have a d phi e dt. D phi e dt. Okay, so compare with the Faraday's law, it is like this: integration of E dot ds, and then equals negative d phi e phi b dt, d phi b dt, like this. Okay, so this means that we have a changing magnetic flux. Changing magnetic flux, there will be induced E field. Okay, here, if we have a changing electric flux, we will have induced B field. Okay, so you can imagine. Okay, suppose the rate of change of this d phi b dt is not a constant. Or let's say if it is a sinusoidal. Okay, something like this. Okay. Phi b 0 and then sine of let's say omega t. Okay, suppose we have a time varying B field like that. You can easily generate that using a solenoid. Okay, in chapter 30 we have learned the solenoid, or actually in chapter 31 we already talk about the transformer, something like that. So which means if you provide an AC source to a solenoid, then it will generate a time varying magnetic flux. And then in that case, taking the derivative of sine becomes cosine. Okay, so this induced E field will be a time varying. Okay, so in that case, I'll go to here. Okay, so it will also generate a time varying E field and then loop back to induced B field. Okay, and then loop back to here. Okay, so it will generate time varying B field generate if it is a time varying E field and then loop back to a time varying B field, loop back to a time varying E field. So that is the why there will be electromagnetic wave 啊？为什么有电磁波的一个简单的解释啊？但严格的数学的话，后面会再讲啊，33章会再讲。Okay, so this is a quick comparison between this induced B field and the induced E field. Okay, so this one is called the Maxwell's law, and then that one is called the Faraday's law. We have already learned that in chapter 30. Okay, so here it says charging a capacitor. So as an example of this sort of induction, we consider the charging of a parallel capacitor with circular plates. The charge on our capacitor is being increased at a steady rate by a constant current I in the connecting wires. Then the electric field magnitude between the plate must also be increasing at a steady rate. 所以它的意思是这里有一个平衡板的电容 ，OK， 然后你就给一个电流进去，给一个电流进去，这个电流是一直给 ，constantly 给，constantly 给的话，那这里的电荷就会增加嘛，就 Q 等于 Q 等于sorry， 应该是反过来I 等于 dQ dt I equals dQ dt. Okay, so if I is a constant, which means that Q is like a linear increasing. It's like if we suppose Q is 0 at the beginning, and then Qt will be like let's say K times I 0, something like that. Okay, so it is like an increasing charge. So if we have increasing charge, which means the charge density is also linear increase. So in that case, there will be in linear increase E field. Linear increase E field, which means suppose we consider there's a cross section, okay, for the capacitor. Okay, so there will be time varying electric flux. Okay, so if we have time varying electric flux, we will have induced B field. Okay, in this case, if this I is linear increase, the induced B field will be a constant. So this is nothing but a constant. Yeah. Okay, so it says that if the current is constant, okay, so the E field magnitude will also be increased at a steady rate. Because if you still remember, the E field is sigma over epsilon naught. Okay, so it has both sides. So sigma over epsilon naught. Okay, so this sigma is proportional to the Q. And this is a constant. Okay, so this E is increased at a steady rate. Okay, so continue. So the E field is direct into the page. Consider a circular loop through point 1, a loop that is concentric with the capacitor plate and has a radius smaller than that of the plate. Okay, so actually we assume this is a capacitor, and then we also assume the capacitor is also a circular plate. Okay, so here we try to draw some Amperean loop. Okay, draw some. So this is the Amperean loop. Amperean loop. Okay, so this is a boundary for the capacitor. This is a capacitor. Okay, so this red one. So this red one is the Amperean loop. Okay, and then the big one is the capacitor. Okay, so we also assume that the E field within the capacitor is uniform, and outside of the capacitor, the E field, the fringe E field is perfectly zero. So that's the assumption, although that's not the practical case. Yeah, but it makes the calculation easier. Okay, so in this case, if we consider the current, if we consider the current is going into the page, okay, here the current is going into the page, so in that case, there will be positive charge accumulate on this plate, and then for this one, okay, and then negative plate on the negative charge accumulate on the right plate. Okay, so which means in the top figure, the E field is from left to right. The E field is from left to right. Okay, here we assume that the current is going into, although the I is not a vector, but we assume that the I is going into the page. So which means that the E field have the same direction as the E field have the same direction as the current, So so in that case, we assume that this I is positive, which means that E is increased linearly. E is increasing at a steady rate. So in that case, we can use right-hand rule to determine the induced B field. Okay, so you use the thumb pointing into the page, and then your forefinger will be like clockwise, something like this. Okay, so still we use the right-hand rule to determine the direction of the induced B field, which is clockwise. Okay, let's say for point 1, it is pointing to the right, this one pointing downward, so on and so forth. So because the E field through the loop is changing, the electric flux through the loop is must also be changing. Okay, so this is what I've said. According to the above equation, this changing electric flux induce a magnetic field around the loop. Okay, so this one is a linear function to the time. Okay, so which means that time derivative will be a positive constant. So in that case, this one is also a constant. Like this. Okay, a positive constant. So in that case, so the loop is like clockwise. The loop is clockwise. Okay, so here we have a quick comparison for the Maxwell equation and the Faraday's law. So of course they look similar. Okay, on the left side is a line integral for the B field. For this one, the line integral for the E field. And then on the right side, we have for the Maxwell law, we have the time derivative to the E field electric flux to the electric flux. And then on this one, for the Faraday's law, we have the time derivative to the magnetic flux. Okay, so these 2 points are the similar stuff. Okay, between these 2 laws. Okay, so here it mentioned that they are similar but different in 2 ways. Okay, 有2个地方不一样. Okay, so the first one is that for the Faraday's law, we don't have anything multiplied by this one. Okay, of course, if you have a multiple turn, you have capital N. Okay, you have number of turns here, but here we just try to ignore this number of turns. Maybe sometimes you can even absorb this N into the magnetic flux. Into the magnetic flux. 就是之前有时候它会有一个式子是乘以那个大写的 N 就是那个圈数，那如果有时候你甚至可以把 n 吸收到这个 phi e 里面，所以让这个式子看起来简单一些。因为通常你看文件里面，它很少把那个 n 写出来的，很少把它写出来的。那它另外写了一个有 n 的式子，是提醒你说，哦，万一你真的是有几圈的一个线圈的话，那你就要记得把那个圈数考虑在内。但是一般你大概找这个 Faraday's law 的话，一般都不会用那个。OK， 所以它这边的话是没有乘任何的常数在前面。But for the Maxwell's law, we have mu naught epsilon naught. Okay, so the two most important constant in the electromagnetism. So one is the permittivity, one is the permeability. 一个是导电率，一个是导磁率，都乘在这个式子里面。一个 mu naught， 一个 epsilon naught。Okay, so mu naught epsilon naught appear for matching the SI unit. 它这里的说法是让两边的 SI unit 是匹配的因为这边的话你不用乘任何的东西，这两边的那个 SI unit 是匹配的。这里是乘完之后它才匹配，但这个数值本身是有关系的，这个数值本身是有关系的。这两个乘起来跟一个很重要的常数有关的，跟一个很重要的常数有关。我们下一章会说到Okay, so for the next point, the negative sign for the Faraday's law means the induced electric field is counterclockwise. If the B field direct into the page and is increasing, okay? 所以这个负号另外一个不同的地方是这里是正号，这里是正的，这里是负的那这个的话就是我们知道这个叫做 Lenz law 嘛Lenz law 那就是有个负号，所以如果在下面这个情况 so for the bottom case, if the B field is pointing into the page and is increasing, the induced E field is counterclockwise. But for the Maxwell's law, in this case, if the E field is pointing into the page and increasing, just like this one, the induced B field will be clockwise. Okay, this is opposite to it due to this negative sign. Okay, so for this negative sign, using the right hand rule is pointing into the page and then like this, so clockwise. With this negative sign, okay, it tells you that the direction is the opposite. So which means in this case is counterclockwise. So this one is strictly follow the right hand rule. Okay, so your thumb pointing into the page, your other four fingers are like going in clockwise. Okay, so yeah, so this is a quick comparison between the Maxwell's law and Faraday's law. Okay, so another question is in chapter 29, okay, we talk about the Ampere's law, and in this chapter we talk about the Maxwell's law. Both of them have this line integral on the left side, okay, but for the Ampere's law, okay, we have this mu naught I enclosed, okay, and then for the Maxwell's law we have this stuff. Okay, so yeah, we need to have two individual laws, two individual equations. Okay, so when should we pick the first one? When should we pick the second one? Okay, so for the physician, they try to combine them together. So they just add them together. So on the left side, it is still induced B field, but it can be induced due to according to two different sources. Yeah, the first one is a static current. Okay, for the static current, if you have static current, it will generate B field. This is what we have learned in chapter 29. Okay, using the Ampere's law. But here, if we don't have static current, rather than that, we have a current going into a capacitor. Okay, going into a capacitor. Yeah, so in that case, we will have this one. We will have this one. Okay, this source will also generate the B field. Okay, so they just try to combine these two into a single equation, and then so this is called 大人的话就全部都要嘛，所以我们的话就是两个都要。Okay, so this one is like the PPAP. So we try to call it the Ampere-Maxwell's law. Okay. So yeah. So this is line integral. This is the static current part. This is the we'll call it the displacement current in the next page. 因为怎么说，就是如果是中学学物理的话，如果学到电路的部分，他就告诉你说，就是如果是 电容的话，其实没有电流能够通过，但是其实的话它也不完全是那样，因为如果你就算给一个直流的话，它也是有一个充电的过程，让它充到某一个电压，就是在27章的时候，我们有推导那个 RC circuit 嘛 ，RC circuit 的话，你就算给一个 DC source， 你还是会有一个 first order 的 exponential function 的 decay， 所以它还是会有电流。但是如果你给一个 AC source 的话，就是像31章所说的，你给一个 RC 电路给一个 sinusoidal 的话，它输出还是会有 sinusoidal， 那它的电流就是进进出出的话，就是它就类似是比如说你有一个 AC source 给一个 RC 电路。当我们计算的时候，我们就还是会说这里是有个电流这里是有个电阻，那我就可以算出来这个 I 是一个什么 sin of 什么什么，它有一个相位，有一个振幅。那其实那个电流的话是进进出出的，因为那个 sin 或者 cosine 的话，它有一个半个 cycle 是正的，半个 cycle 是负的，所以半个 cycle 在充电，半个 cycle 在放电，所以它其实你可以看成它还是有电流通过这个电容，但是实际上它没有电子穿过去而已，只是说它看起来是进进出出，那让这个 I 没有断掉它就是还是维持着一个 sin 的状态，只是说这个电荷在这个电容里面可能累积到正的放电回来，累积到负的又放电回来。在单一个板上面，它就会有正的、零的、负的时候，一直来回，所以如果说交流的话，我们还是会认为它是会通过这个电容或者电感的。So here it says when there is a current but no change in electric flux. No change in electric flux means a DC current. Such as with the wire carrying current loop constant current. The first term of the right side of equation is 0, and so the equation is reduced to Ampere's law. So there are two cases. So for the first one, if there is only static current, then the second term will become 0. It shrink down to the Ampere's law. And then for the second case is that if there is no static current but only change in electric flux, so the first term will become 0, such as inside and outside the gap of a charging capacitor. The second term of the right side of the equation is 0. So I think there is a current but no change in electric flux. So I think this should be second. This should be second. This should be first. So this one should be the other way around. This one should be, yeah. 因为这个的话是如果只有静态电流的话，是第二项为0，它就会变回来 Ampere's law。那第二个情况是没有静态电流，只有电场的改变的话，那第一项为0，它就会变成 Maxwell's law。所以你就不用想我先把整个放出来，我再看有没有静态电流或者有没有那个改变的电场，改变的电那个叫做 electric flux 那个电通量，改变的电通量再看到底是第一项为0还是第二项为0从而它就会缩减回去 Ampere's law 或者是 Maxwell's law 大概是这个意思。So and the equation reduced to Maxwell's law of induction. So let's have a